In order to load the shift register at once, all the bits at once, we can have the parallel load capability introduced into the shift register. In order to do that, we can have a multiplexer between each shift register stage, and then the data could be selected whether to be loaded directly or whether to be received from the other stage of the shift register. So you can see indeed the structure over here. Let me explain it to you. We have two flip-flops, A and B. What we see over here is indeed a multiplexer, 2 to 1 line multiplexer. If you go into the details, let's see it for A. For A over here, we can see that shift is used as the select input of the multiplexer. So if shift is equal to 0, let's see what happens. When it is 0, we will have 0 as the input of the AND gate over here, so the output will be also equal to 0. And then since shift is equal to 0, we will have 1 here, and the output of the AND gate over here will be DA. As a result, the output of the OR gate will be also equal to DA. So when shift is equal to 0, the input to the flip-flops will come from DA, and similarly for the B, it will come from DB. And then when there is the rising edge of the clock, this data could be loaded into the shift register. On the other hand, if we have, let's say we have shift equal to 1, when shift is equal to 1, I show it for B this time. When shift is equal to 1, we will have 1 here. Over here we have A, and therefore we will have A here at the output of the AND gate. For the other AND gate, we will have 0 as one input, therefore it will be 0, and then as a result, the input to the B flip-flop will come from Q of A. Therefore, when we have the rising edge of the clock, this time we will shift towards right. So shift right will happen. For the A flip-flop, it will receive, this time in will be provided at the input of the A flip-flop. So new data will be inserted into A, and then A's value will be copied into B, and then B's value will go out. So when shift is equal to 1, we will have shift right. When shift is equal to 0, we will have parallel load. New data will be loaded into the shift register. We can extend this into multiple bits indeed. Over here we have only 2 bits, but we can have more bits, and we can make n-bit parallel load shift register. However, we don't want only to have the shifting and loading capabilities, but we want to store the data whenever we want. So we can store the data, then when needed we just shift it, and when needed we just load it with some in the parallel form. To perform that, the structure is changed here. It is modified. We have the parallel load shift register with the no change capability as well. So now we kind of have 3 operations: no change, load parallel, and shift down from Q0 to Q3. And we have 4 bits over here. Yeah? In order to determine which one of these should be performed, now we have 2 control signals. Not only the shift, but shift together with the load. Let's see what happens when both of them are equal to 0. When shift and load both are equal to 0, let's have a look here at the structure of our circuit schematic. Shift is equal to 0, so we'll have 0 here. The output of this inverter will be 1. We have 0 here, 0 here. If you can follow me, we have 0 over here and 0 here. So the output of those AND gates will be also equal to 0. 0, 0, 0 here and 0 here. For the load, we also have 0. So we have 0 here. The output of the load will be equal to, output of the inverter connected to the load will be equal to 1. Then 0 is also applied here. 0 is here. 0 is here and 0 is here. So therefore the output of the second AND gates will be also equal to 0. Let's see what happens to the output of the third AND gate for each bit position. So we have 1 here, therefore 1 will be available here and there. We have 1 here, 1 here, 1 here and 1 here. On the other hand, from the shift, which was equal to 0, we have 1 over here. That 1 will be also available at the input of those AND gates. So we have 1, 1, 1, and 1. The third input to these AND gates comes from the output of the flip-flops themselves. So we will have Q0 here. Over here we will have Q1, Q2, and Q3 obviously. And therefore the output of the AND gates will be Q0, Q1, Q2, Q3. The other two inputs to the OR gates are equal to 0. Therefore we'll have Q0 as the output of the OR gate Q1, Q2, and Q3. And you can see that when the rising edge of the clock arrives, the content of the flip-flops will remain the same, and therefore no change will happen in this case. We can also consider the other two cases. Let's go through the second one. When we have shift equal to 0 and load equal to 1. Let me just clean this up. Okay, nearly there. Alright, so we have shift equal to 0 and load equal to 1. Shift is 0 and load is 1. When load is 1, the output of the inverter here will be equal to 0. The output of this inverter over here will be equal to 1. And now if we follow, we have 0 here, 0 here, 0 here, and 0 here. And therefore the output of the corresponding AND gates will be equal to 0. So the third AND gate for each stage will give us 0. On the other hand, since shift is equal to 0, the output of the first AND gates will be also equal to 0 because it is directly connected to the shift. So we have 0, 0, 0, and 0 over here. For the second AND gates, let's see what we have as the input. We have 1 from the shift and we have 1 from the load. So the first input to the AND gate and third input to the AND gate is equal to 1, and the second input comes from D0. Therefore the output of the AND gate over here will be equal to 0. Similarly, we will have D1, D2, and D3. And then you can see that the output of the OR gates will also follow D0, D1, D2, D3, and then at the next rising edge of the clock, Q3 will be equal to D3, Q2 will be equal to D2, D1, and D0. And this is indeed loading the shift register with some new data. So we have loading of the data in a parallel way. The last thing is when we have shifting. Let's consider that as well. Let me just clean this up. So when we want to have the shifting, shift will be equal to 1, and then the value of the load doesn't matter. Let's see how it works. When shift is equal to 1, we have 1 here and 0 here as the output of the inverter connected to the shift. And now if we follow this 0, 0 is connected to the input of the second and the third AND for all bit positions. So the outputs from the second and third AND for each bit position will be equal to 0. For the first AND, we have 1 here. We have 1 here, 1 here, and 1 here. So one input is equal to 1, which comes directly from the shift. The second input for the first bit position comes from the serial input. If I call it SI, we will have SI here. Therefore, the output of the AND gate will be equal to SI, and the output of the OR gate will be also equal to SI. Then for the second bit position, we can see that the first input to the AND gate comes from Q0. So the output will be equal to Q0 because it's Q0 and 1. The OR will give us Q0. And similarly for the next bit position, we will have Q1, Q1 here. And for the last one, we will have Q2 here, Q2 as the output of the OR gate. So when we have this situation, after the next rising edge of the clock, Q3 will be equal to Q2, Q2 will be equal to Q1, Q1 will be equal to Q0, and Q0 will be equal to the serial input. And in this way, we will have shifting down from Q0 to Q3. And you can see that in this case, the value of the load doesn't matter, okay, because we kind of referring to the shift value, we could see that the output of the AND gates which are connected to the load are already equal to 0.